A number system is a set of symbols used to represent values derived from a common base or radix. So what is a common base or radix? Common base or radix is the unique symbols that we can see in our number system. For example, in binary number system, we only have 0 and 1. So definitely, base or radix is equals to 2 because there's only 2 unique symbols. So we can convert each number system into decimal numbers with the help of this notation, base raised to I, where I starts at 0 and increases by 1 from right to left, and base as the number of unique symbols in a number system. Number systems can be classified into 4 major categories. So the first one's binary number system, octal number system, decimal number system, and also the hexadecimal number system. So let us first discuss the binary number system. Inside of our computer, the data or user input is converted and transmitted as electrical signals, which can be represented using binary number system. Binary number system uses 2 unique symbols, ones and zeros. These ones and zeros represent the state of a wire if it's open circuit or closed circuit. So using the notation a while ago, which is base raised to I, we can now easily convert binary values to decimal number system. So in this case, base is equals to 2 and then raised to I. So we will make a table for this, where I has a value of 0 up to 7 and our base, which is 2. So notice that when we raise 2 to 0, the initial value of I, it gets 1. 2 raised to I, if I is equals to 1, is 2, up to 7. So convert binary to decimal. Before we convert binary to decimal, let us have a quick definition. What is a decimal number system? A decimal or base 10 number system has 10 unique values ranging from 0 to 9. This is the most commonly used number system all over the world. So in order for us to convert a set of binary numbers, we need to use this table above. So the first thing that we have to do is to copy this table, add a new row, and copy the value of the given binary. So in this case, we just copy the given binary number or value, and then ignore the first row. After that, we will multiply each value to its corresponding decimal value. So 1 times 1 is 1, 2 times 0 is 0, 4 times 1 is 4, 8 times 1 is 8, 16 times 0 is 0, 32 times 1 is 32, 64 times 1 is 64, and 128 times 0. So we don't have to put or to include all the values that has 0 because we're just going to add the values that we have obtained from multiplying these values. So even if we add those zeros, it will not have any effect on the result. So after adding this, we will get 109 base 10. And that's how we got our answer. So let us try converting decimal to binary. Let's just say we have 205 base 10 to be converted into binary. So the first thing that we have to do is to look at our table and get the maximum value of our base, which is 128. And then let us compare it to our decimal number. So is 205 greater than 128? If yes, we have to annotate 1. So we have 1 here. And then deduct 128 to 205. That's why we got 77. we will compare the 77 to the next value of our binary, which is 64. So is 77 greater than 64? If yes, we will annotate again 1 here. And then deduct 64 to 77. So that's why we got 13. And then again, we will move to our next binary value, which is 32. So we will compare, is 13 greater than 32? If yes, we will annotate 1. But in this case, 13 is less than 32, so we will just annotate 0. And we will not deduct a number to 13. We will just have to bring it down. And then compare it to the next value of our binary, which is 16. Now, is 13 greater than 16? Again, it's not. So we will annotate 0, and then we will not deduct any number to 13. We'll just bring it down. So as we continue or we go on, we will get these values. Is 13 greater than 8? Yes, we will annotate 1. Deduct 8 to 13, we will get 5. And then compare 5 to the next binary value, which is 4. Is 5 greater than 4? Yes, we will annotate 1. And we will deduct 4 to 5. So we will get 1. Is 1 greater than 2? No. So we will annotate 0. And then we will just bring down 1. And since this special case, which is 1 is equals to 1, we will just annotate 1 at the last part. So after getting these annotations, we can now rewrite our answer, just like this. So that's how we got our binary number out of the decimal number. Now let us try to convert binary number system into hexadecimal number system. But first, let us define what is hexadecimal number system. Hexadecimal number system is a base 16 number system that consists of 16 unique symbols ranging from 0 to 9 and A to F. So you can think that this is just an extension of the decimal number system. This is used to shorten large representation of binary values, and most of the time, it can be seen as a value of a color in a color palette. So here's an example. Here's a color palette of Facebook. So as you can see here, there's the hex color or hex value for each color. So this is used widely in computer programming languages, and I think that's JavaScript and Java, but it's not limited only to those programming language. So here we're not going to use this table, but instead we're going to use this. So the first thing that we have to do is to copy the given binary number, the 11010101, and then separate these values by dividing them into 4 bits. So the first one is on the rightmost side, so we'll divide 4 here. We get the 4 group of 4 bits here, and then place it on our rightmost side, 0101, and then the rest, since this is a divisible by 4 bits, so the rest would be placed on the left side. And then after getting these values, we will locate or compare the binary values and then get its equivalent hex value. So in this case, 0101 is equals to 5, so we will just write it down. And then the next one is 1101, which is equivalent to D. We will just have to write it down, just like before. And then after getting these values, we will just merge it. So that's how we get our answer, D5 base 16. Now, how are we going to convert hexadecimal value into binary? So for example, I have given you C5A. We can use this rotation, or we can use this solution, but this time we will just reverse the process. So in this case, C5A, we will separate each symbol or hex symbol, And then from our table, we will just locate the value of A. So here, we see that A is 1010 in binary. So we'll just write it again. So 5 is 0101. And then C is equals to 1100. And then just merge it. And that's how we got our answer to C5A, which is converted into binary number system. So now, let us try to convert binary into octal. And here's a quick definition. What is an octal number system? So octal is consist of 8 symbols ranging from 0 to 7. So this is useful in earlier computers which can process bite-sized data. So here, let us try to convert 100,110 base 2 into octal. So we will not use the table for binary to hex, but instead, we're gonna use this. So in octal, we can use 3 bits in order to represent each value of octal into binary. So just like in hex, we will just copy the value of the binary and then separate by dividing these bits by 3. So at the rightmost side, we have 110, and then the left side, we have 100. And then just like in hex, we will just locate the value for 110, and that's 6. We will just write it down. And then 100 is equals to 4. Just like before, we will just write it down, and then we will just merge these two. That's how we get 46 base 8. Now, how are we going to convert octal to binary? Let's just say I have given you 230 base 8. So now try to convert this into binary. Again, just like in hex, we can use or we can just separate the symbols and then locate the value of these symbols into binary. So 0 in this case is 000. 3 is equivalent to 011, and 2 is equals to 010. After getting this value, you'll just have to convert them or merge them. And that's how we got our binary value out of that given octal number. Now, let us try to convert octal number system to decimal. But in this case, we're not gonna use this table, but instead, we're gonna use this. So remember a while ago, we used base raised to I in converting base 2 number system into decimal. So since we're converting octal to decimal, we will use that base raised to I notation again. Okay, so I think you know how it works. So 8 raised to 0 is 1, 8 raised to 1 is 8, and so on and so forth. So we're just gonna use this to convert octal to decimal. So the first thing that we have to do is to copy the table and then add a new row, and then the given 370 will be placed on the rightmost side of our table. So the 0, so it comes in the first place value, just here, and then the second one is 7, that's why it's here, and then the third one is 3, which will be placed here. So after placing this value, we'll just have to multiply them on the value of base 8. So here we got 8 times 7, or 7 times 8, and 3 times 64. We don't have to include this 1 times 0 since we're going to add them later on, and getting 0 or adding 0 does not give an effect on our result. So 8 times 7 is equals to 56 plus 3 times 4 or 64 is equals to 192. So that's why we got 248 base 10. And as you can see here, class, after we convert octal into decimal, the 370 or the constant 370 becomes 248 because the constant becomes lower when we convert an octal to decimal. So same goes for decimal to octal. If we convert a decimal value into octal, the constant becomes the value of constant becomes higher. So we will see that here in our example. So let's just say I have given you a decimal number system or 122 base 10. We will convert this 122 into octal. So just like what I have said a while ago, I am expecting that we will get a higher value of constant here since we're converting decimal to octal. So here's how we convert decimal to octal. So the first thing that you have to do is to copy this given and put it in here. After copying it, divide it by 8. So we got 15.25. So the whole number here, we'll just copy the whole number here and then place it down here. And then the 0.25, we will just multiply it by 8. So we got 2. So annotate 2 here. And then this 15, we will just divide it by 8 again. So we got 1.875. So this one here, we'll just put it in here. And then the remaining 0.875, we will just multiply it by 8. So we got 7. And then the last one, 1 divided by 8 is 0.125. Since this 0, we don't have to put it in here since if we divide 0 by 8, we will just get 0 as a result. So we'll just multiply it by 8. So 0.125 times 8 is equals to 1. So that's how we got our octal number. But how do we write this in our solution? So we'll just write this upward. So that's the case. Our octal number is 172. So notice that the result or the constant is higher than the given. Okay? Now let's see how are we going to convert octal to hexadecimal. So given 213 base 8, we will have to convert it into hexadecimal. So the first thing that we have to do is to convert octal to binary and then that binary into hexadecimal. So the binary number system will serve as a bridge in order for us to convert octal into hexadecimal. So the first thing that we have to do is to copy 213, and just like what we have discussed a while ago, we'll just locate the value of each separate symbol. So 3 is 011 and 1 is 001 and 2 is 010. After this, merge them into 1. After merging them, we will divide and separate them into groups. And using the table of binary to hex, we will get 8B base 16. And that's how we got our answer from 213 base 8 to 8B base 16. So how about this one? Convert hexadecimal to octal. So we will just reverse the process that we have taken from octal or converting octal to hexadecimal. So in this case, 83C, we'll just locate it on our table. We'll just convert them into binary. So after getting this binary, we will merge them, divide them by 3's, and then look for our table. 100 is 4, 111 is 7, 000 is 0, and 101 is 5. And then just merge them as it is. So that's how we got our octal value out of that hexadecimal value. So now let us have this one. Convert hexadecimal to decimal. So here I have given you A7 base 16, and we have to convert that into decimal. So what are we going to do? So first, a while ago, we used the base raised to I to convert binary to decimal and octal to decimal. So this time, we will also use that. But this time it is hexadecimal. Now, so how do we create that? So just like what I have discussed in our octal and binary, we will just raise them into 0 from right to left with increasing value of 1. So 16 raised to 0 is 1, 16 raised to 1 is 16, 16 raised to 2 is 256, and so on. So I just added an ellipsis here because it yields a very high value which is not which cannot be contained here in our cell. So I just displayed the 0 to 3 instead. Okay, so the first thing that we have to do is to consider this table at our right side. So use this only when there's a letter in the given hex value. So our given hex value is A7. Okay, so based from our table, A is equivalent to 10. Okay, so what's the next step? So we now have the information that A is 10, and then separate 7 to 10. After that, just place 7 to the first cell of our binary value, and then 10 to the next one. Just like this. And then multiply 1 times 7 plus the product of 16 times 10. So that's why we got this. And then after getting the result, 10 times 16 is 160 plus 7 times 1 is 7, we have 167 base 10. So hexadecimal to decimal, A7 base 16 is equals to 167 base 10. Now let's try converting decimal to hexadecimal. Suppose that we have 87 base 10. We want to convert that 87 into hexadecimal value. So how are we going to do that? So the first thing that we have to do is to divide 87 to 16. So we have 5.4375. We will just bring down 5 and multiply 0.4375 by 16. So we have 7. So we'll just annotate 7. And then the 5, we will just multiply it or divide it by 16. That's how we got 0.3125. And then this 0.3125 will be multiplied to 16. So that's how we got our answer, 57 base 16.